So, our last speaker is a familiar face to those of you who have come to this conference before, Dr. Leigh Orf from the UW. And these are always interesting videos that he shows because he researches severe thunderstorms and tornadoes, but from a computer standpoint, and being able to model that. And this is where the science is going. You know, it's one thing to have video representation and pictures. I mean, that all helps, but we have to get to the point to where we can understand these storms at as small a scale as possible to be able to predict them and predict what they're going to do in the future. And a lot of what Dr. Orf has been doing is making its way from the research stage into where we're going eventually when it comes to the warning and forecast process. So, Dr. Orf.
All right, great.
Stage is yours.
All right, great. So, thank you very much for coming. My name is Leigh Orf, and I am a scientist at, where's that microphone? Here it is, it's right in front of my face. I'm a scientist at the Space Science and Engineering Center, where Tim is, who gave the satellite talk. I work for SIMS, which is sort of part of this sort of a subunit. And yes, my research is on, essentially it's basic research on supercells. And I'm using supercomputers to simulate them. What that means is we essentially take very sophisticated models that, to the best of our ability, use the laws of physics to basically forecast the future of the atmosphere. This is done with our climate models. This is done with all sorts of models in the world. It can be done on tornadoes as well and supercells. So I'll talk to you today about some of this work, and I'm also very interested in getting these storms to look like the real storms. What I mean by that is I'm able to use techniques of visualization that give us insight, that peer into the storm, peel layers off of the storm, and look into it. So the basic questions I'm exploring here are, how do some tornadoes form in supercells in the first place? Okay, it's a very difficult issue. We've tried different proxies for tornadoes. We look at TVS signatures. We look at these new tornado debris signatures, which are excellent. In this case, it's something that you're seeing after the fact. We'd like to be able to predict these better. We'd like to be able to look at a radar image or maybe a forecast and say, where are the storms going to produce tornadoes and where are the storms not going to produce tornadoes? So these are outstanding questions in the field of mesoscale meteorology. So unlike many folks who do field work, I'm almost entirely inside the computer. That's just kind of what scratches my itch. I enjoy programming. I've enjoyed programming since I was in high school. When I was very young, in Massachusetts actually, if you want to talk about a real storm, October 3rd, 1979. Anybody remember that one?
I was there.
Windsor Locks. I lived in Ludlow, or Feeding Hills at the time, just north of the Connecticut border in the Connecticut River Valley. That storm basically dissipated over my house, or very, very much in the area. I was in 6th grade, and I remember kids doing posters about the tornado and drawing pictures of little swirly things. A few years earlier, my house got hit by lightning. This is again in Western Mass. Not exactly a hotbed of severe weather, but it seemed to find me. So I got interested in this, but eventually I met computers, and then it was game over, because I knew I wanted to do computer work, and then when I came to college, I discovered you can take computers and do weather? Oh, I'm right where I want to be. Okay, so over the course of many years, I got more interested in computing and then started to do work with parallel computing, which requires supercomputers. And when you basically, it's the nice way of divide and conquer. You know, we're in Wisconsin. Divide and conquer has been used in some ways to be like a bad thing. But when it tries solving a problem on a supercomputer, essentially you're breaking it up into lots of pieces, but what you're conquering is the physical problem. You can do things with supercomputers that you simply cannot do with standard computers. So you're going to see a whole lot of really cool looking animations. These are just volume renderings or visualizations of the data on the computer. We're getting to the point now, when I say we, I mean my research team, of answering questions more quantitatively and publishing in journals and things like that. Why are we studying these high-end storms? So I'm interested in EF5, EF4s, preferably the ones that are on the ground for a long time. I can count on both hands. The last maybe 30 years, we've had maybe 10 of those. If you're from Wisconsin, obviously, and you know about the Barneveld tornado in 1983, F5 wiped out the entire town. You go on west and you drive by that town, and none of the houses are older than 35, 40 years. So this does happen in Wisconsin. So it's kind of obvious why we want to study these storms, but one thing that is not obvious is that we're really bad at forecasting them. We've heard about all sorts of amazing technological breakthroughs in observational meteorology. We're on the cusp of this. We're on the cusp, I think, of being able to say things like, this supercell is probably just going to, maybe produce a very weak tornado like the one on 151 and be done. That wasn't even a supercell, by the way. But maybe it's going to be a long track EF5. And that's the kind of forecast we need to be able to make, because those are the ones that do just the most devastating damage. So I'm looking at the top end tornadoes. I'm trying only to study those. I'm not trying to say that what I'm doing applies to all supercells and all tornadoes. No, I'm only looking for these high end EF5 long track storms. So how do you do this? I'm using a cloud model, which is a computer program that essentially follows the laws of physics and forecasts the next few seconds in time, or a fraction of a second in time. Using this process, we can watch the cloud grow like we're growing. Maybe you're in a laboratory growing something from a culture. In this case, the computer is the laboratory and you're growing a storm. So you need, in order to do this the way I'm doing it, you need to sample the atmosphere pretty faithfully. In this case, we didn't use a Rayab balloon launch to initialize the model with the atmosphere. We used another model forecast to initialize the atmosphere. So it's models all the way down in a way. But the truth is, what we feed those models is observations. Rayab, infrared, satellite imagery, all the remote sensing techniques get fed into what's called an assimilation process that then gets into our forecast model. So it's not that important, but what is important is that we try to simulate a real event, or at least to the best of our ability. So this isn't just a theoretical supercell. This is trying to be as close to 24 May 2011, EF5 that occurred in El Reno, as possible. Okay, so what do you need to do this? You need a good, garbage in, garbage out. You need good input. You need a really big supercomputer. The computer we're using is called Blue Waters. It is sponsored by the National Science Foundation, so this is also, thank you, coming from all of our tax dollars. It has over 360,000, what you might say, individual pieces or floating point compute cores. The way these supercomputers work is they're basically multi-core nodes all hooked together with a really fast network. So one piece of Blue Waters is 16 floating point cores, and you have 20,000 of them or more, and then you can do some really interesting things. When you start talking about petabytes, you're talking about big data. And in one way of looking at it, the problem I'm trying to solve is indeed a big data problem at its most basic. I've got a lot of data, and I'm trying to understand what's going on inside that data. Much of the work that I have done has been with getting, fine-tuning the model so that I could save data enough to make these cool pictures and stuff. Because from my perspective, I've always been very interested in visualization, in bringing the computer simulations to life. And to me, that is the first step at trying to understand what's going on. It's a very important step. You need a bit of luck, just like going on a chase. When I fire up a job on a supercomputer, it might not produce a tornado. I'll probably get a supercell, but I might not get a tornado, just like when you go out chasing. So if you're wondering what the size of this problem is, it's pretty big. The simulation that I'm going to be spending most of my time talking to about is about 2 billion, with a B, grid cubes. Okay, so if you're looking at arrays, if you're a program and you're looking at your array sizes, those are your array sizes basically. But the good news is we split those arrays up amongst many different computers within the Blue Waters computer. But I've gone up to 15 meter grid spacing. You'll see some of that. That's 18.4 billion grid cubes. Notice that it doesn't go linearly. When you go from 30 meters to 15 meters, it's not 3.6 billion, it's 18.4, and that's because you're increasing the resolution in 3 dimensions. So the storm I'm looking at occurred 24 May 2011, and I'm not claiming to model that specific storm, but we did the best we could to bring it to life using the environment surrounding it. We have an EF5 tornado in the computer for an hour and a half, and I've done many simulations of this environment, and sometimes the tornado only lasts an hour, sometimes it goes as long as 2 hours. Long track EF5. Lots of rotation in the storm on very small scales, what you might call mesocyclones if you're technical about it. A mesocyclone would be a very small vortex maybe on the order of dozens of meters across. These things are abundant in these simulations, as you'll see. We see lots of vortex mergers going on where you have vortices following the forward flank, the downdraft boundary of the storm, where you might see the tail cloud streaming in, merging together, and ultimately leading to a tornado. And it's kind of silly for me to sit and talk about this, but I want to tell you first before I show it to you, because you'll see it better than I can explain it. We have identified a feature, my research colleagues and myself, that we're calling the streamwise vorticity current, which, if you're a storm chaser, might be at least roughly related to the ghost train. We've talked about the ghost train, which is simply a term for the very, very strong inflow that sometimes goes into supercells. In order to maintain a super strong updraft, you got to pull air from somewhere. Sometimes it's coming from where you are, and you're going to get sucked into that storm if you're not careful. So the SVC seems to be very important in the storm's morphology. So, enough of the words. Let me talk about looking at some real storms and then comparing it to the simulation. So I'm going to kind of show you some footage, and I'm going to show you some simulation work. All of the footage was taken by other people other than me. I give everyone credit, but keep that in mind. I'm mostly in the computer. So we've done a lot of storm chasing, a lot of observational work with supercells and tornadoes. Let's take a look at some real ones to get our sort of our basis here. So some of the footage I'm going to show you is from Hank Shima. He's Picos Hank on YouTube. I encourage you to subscribe to his channel. He's one of the he's a very, very interesting fellow and a very, very good photographer, videographer. He takes some wonderful pictures of supercells and tornadoes. So here's one we're showing some of the general supercell characteristics. Rotating updraft, which is a fancy word for that, is mesocyclone. The tornado beneath that mesocyclone, you can see some what appears to be debris near the ground underneath the tornado, and an inflow band or something looking like a tail cloud. And beneath that inflow band, you can see a little rain foot. That's the forward flank of the storm, and that turns out to be a very important part of the storm in my simulations. Here's another picture of an actual supercell. You can see this big wedge tornado. You can see air from the right streaming in. That's the tail cloud again. You can see the rear flank. In fact, I've annotated all these. I can show you that. These are the different components. And I'll do this repeatedly to sort of get our bearings here. So, why did I show this particular picture? It's kind of hard to see with the contrast, but the tail cloud here is very obvious. It's a very low streaming in cloud that is feeding and sort of rising into the storm. This looks a lot like a feature that the SVC feature that we're talking about, and it's certainly roughly in the right region for that. Now, this is one of my simulations. So what I've done is I've taken a piece of the simulation, because it's much bigger than what you're seeing here, just to show you the same kind of perspective. So there's our tiny little tornado, or tiny with respect to everything surrounding it. Here's your tail cloud, your mesocyclone, your updraft, your rear flank, and your forward flank. So hey, that's pretty good. It looks like those features look a lot like the ones we just showed you in the other movie, the actual photographs. I couldn't not show some GOES 16 stuff, because even though I'm in the computer a lot, this stuff jazzes me like you can't believe. We can now see these storms on a much faster scale. You've got 1 minute data. You can see gravity waves sort of like a dropping a stone into a pool, watching them shoot out from the overshooting tops. You can see all sorts of neat stuff. Talking to Tim earlier, he said, oh, there's this feature that people think might be associated with extremely strong updrafts that occur. So I am looking forward to doing more with observational data in order to, because ultimately I want to understand more about tornadoes. And you need multiple ways of looking at it. But one of the things to also keep in mind when you look at this kind of image is how many different storms you see. Real outbreaks can be made very complex by multiple cells in one area. Those types of interactions can make forecasting a real challenge. You don't typically get the isolated supercell just doing its thing. Now, I'm going to show this over and over again. This is a loop, because that motion, I want you to sort of be thinking of this motion. What do you see here? You see a rotating wall cloud. You see a tail cloud streaming in, the forward flank, and there's the rain foot. So this is the forward flank of the storm. This tail cloud forms along the boundary is where the cold air from the storm's outflow meets the air ahead of it in the environment. Here's another loop, okay, the same basic thing. Tail cloud, kind of a small one, forward flank, rear flank, wall cloud rotating, tornado descends out of the wall cloud. What's going on? What makes that tornado form? Why did it form then? Why didn't it form earlier? Why did it form at all? These are the kind of questions that we're trying to answer. And notice the explosive upward growth of the cloud field here. The updraft, everything you see here is in an updraft, basically. Okay, so let's take a peek. So here's the storm as seen from like a couple hundred kilometers. This shows you the full domain of the simulation that I'm spending a lot of time focusing on. I'll sort of come closer and closer to give you a sense of scale. Keep in mind, in order to resolve that so-called tiny tornado, we need to have hundreds of grid points or grid cubes that cover that little tornado. So this kind of gives you an idea of how much computer power you need, because we have that same amount of resolution over almost the whole storm. This is a cool visualization done by David Bach at the National Center for Supercomputing Applications. Here's the model grid. There's the storm looking at it from aloft where the satellite would see it. There's the overshooting top. He's done some very nice things with volume rendering to show he's focusing on the cloud field, so you'll see things like Madison clouds. You won't see any rain, he hasn't shown that, but the explosive upward growth of these cumulus turrets and things you see here and the Madison type cloud features, these all give us great confidence that this kind of simulation is doing a fairly good job of looking like the real atmosphere. Okay, now recently, so this is some new stuff I've done, same basic environment, but I've gotten better at saving data. And that may seem like a very boring thing to say at a tornado talk, but I have saved every model time step of this simulation, and the model time step is 1/6 of a second. And what I'm doing here is I'm showing you all those time steps. There is nothing more I can possibly show you here because I've saved it all. What I'm doing is I'm taking the cloud field and I'm shading it by rotation. So where you see these glowing regions of rotation are regions in the cloud where the cloud is rotating. So the cloud might be rotating like it would be in a tornado, but it could be rotation on its side as well. I'm just looking at the vorticity magnitude. Now, you see stuff streaming off from the right to the left. This is the forward flank. This is the mesocyclone's right about here, and this is the developing wall cloud. And keep your eyes right about here because you see these little glowing bits will kind of come and go. At some point, you're going to see a tornado descend from that region. So this is done. I've done this. Now it's going to be a blue tornado because it's a blue NATO. I shaded it by the amount of rotation, and of course the tornado itself has a ridiculous amount of rotation into it. So here it is descending towards the ground. This would be the descending funnel cloud. But keep in mind, this tornado is already on the ground. Just like we've talked about in some of these earlier talks, the winds of the ground were already at tornado strength before the condensation funnel descended to the ground. So that you have to be very careful if you're looking for visual cues for tornadoes. You can't rely on the fact that there will be a condensation funnel. There isn't always a condensation funnel if the boundary layer is too dry. But you'll still see debris spinning up, assuming there's some debris to spin up. So this, as I've been talking, this thing has just formed a tornado. You still see these little glowy bits coming in. That's rotation, and there is a story to be told about vorticity in this simulation for sure. But this kind of simulation, we've been doing, when I say we, the scientific community has been doing work in this area, three-dimensional cloud modeling, since the late 1970s. But this is kind of pushing it to a new limit, I think. Here again, we're looking at vorticity long before the storm forms a tornado. Here's the major updraft, the mesocyclone. I'm shading it by the updraft, so where you see like it going from gray to yellow to red, it means the air is getting sucked up, which is pretty obvious by looking at it, but it also helps to sort of quantify it a little bit. Now, as time goes on, you're going to see the tornado form right about here. Some of the lighting's a little bit funny, but you'll notice that there's no trigger, there's no magical switch, there's no signature that just shows up, and there's our tornado right now. This will run for quite a while. I'm trying to show essentially the basic structure of what's going on. Keep in mind that the entire storm is moving towards the northeast at about, say, 30 miles an hour. The way we model these storms is we subtract the storm motion out of the solution so that we can follow it along. There was a vortex that grew out of the ground almost and then wrapped around the tornado and then went up the tornado. I'll show you some of this much slower so you can see it better shortly. There's all sorts of fascinating things. Here's the rear flank of the storm. Here's one of those rear flank surges that occurs in the supercell. Now the tornado's been on the ground for a half an hour by now. We still see activity from the rear flank. A lot of the activity you see from the rear flank, however, is air that's scooted around the bottom of the meso from the forward flank. A lot of time when you hear people saying RFD, RFD, RFD when they're chasing, I suspect they're actually in air that may have originated from the forward flank that is coming around the mesocyclone. And now the tornado is taking on a two-celled structure with a downdraft in its center. This has also been verified by chamber models and other models. So everything looks pretty darn good. I mean, there's some issues we have with rain centrifuging and that we don't have it built into the model physics. In the real atmosphere, if you look at a tornado that has rain in its vicinity, you'll have a little hole in the center because the rain, due to its higher mass, gets centrifuged outwards through the air. That type of physics has to be put in the model. It turns out it's a kind of a complex problem. So our tornado has rain in it where it shouldn't be. That's a problem we're going to fix. But again, this thing is on the ground for an hour and a half or more. It's still churning along. There's just so much to be seen and studied in this data. It can be overwhelming at times. Notice how the rear flank sometimes kicks out these vortices and they take several rotations around the tornado before they get sucked up. When you have anticyclonic or clockwise vortices interacting with the counterclockwise or cyclonic tornado, it does all sorts of weird things. Now this thing's dying. There's downdrafts falling down, sort of squashing the tornado. You'll see a lot of horizontal vortices, a lot of kinetic energy is being redistributed. It's not visible in this image, but it's now a rain-wrapped tornado. It's pretty much decay. You can still see evidence of the rotation here. It's still pretty strong, but it's in the process of getting wiped out as it gets completely encircled by rain. So this is basically an overview of the full simulation. And again, if you go to a lot of talks, you often don't get this much video. I've managed to make a lot of video. Here's the streamwise vorticity current that we've identified. This is along that forward flank again. Just watch the particles go. I mean, I can write a paper about this and describe it in words, but I can show this video and you can say, oh, it is moving helically. It is horizontally oriented. It's being tilted. It's being lifted. It's being stretched. It's being brought up. It's all in here. But what we have to do is tag these parcels and trace values of different physical quantities along their path. That's a very powerful technique in meteorology called Lagrangian parcel analysis, where you follow the air around and see the forces acting on it and then try to figure out what's going on. I'll run this one. Some of these will go faster, some of them will go slower. This is, again, showing the generation of the tornado genesis. We're looking west now, so here is the air streaming in from the north. This is that SVC thing that we've identified. Here are those vortices that you would see. This would be the ghost train in this case, if you're thinking in that term. The strongest inflow on the warm side is right along this boundary. A lot of chasers like to hang out in the rear flank of the storm, which is good to be safe, usually, because you're usually behind the tornado. Being south is probably the best visibility-wise, unless you get lucky and you're west and the RFD sweeps out the rain and you get to see the Rochelle tornado. But you know, I'm just a computer guy, what do I know? Now look at this here, several vortices, dozen vortices all kind of coming together. Bizarre. I mean, this is the reason I save data every damn time step is so I can capture everything, because some of this stuff happens pretty fast. Some of this stuff happens on the order of seconds. So by saving all the data, I can go back and reintegrate and reinterrogate this simulation over and over again, and I don't even need the supercomputer to do it. So I spent a lot of time working on this. By the way, the shading I've used is the updraft speed. So what this really shows is that the updraft is getting stronger as you go up, which is what you would expect, but it really highlights that so-called vortex stretching term, where you have existing vertical vorticity through an updraft that will stretch that vorticity to help make it stronger. And it's just one piece of the puzzle, but there's a tremendous amount of vortex stretching going on. And there's our tornado. I mean, while I was talking, it formed. What exactly went on? Why did it form there? Why didn't it form here? How many vortices had to merge before it formed? You know, there's all these questions. And this is just one simulation. I've done dozens of these simulations in the same environment using slightly different model parameters, and sometimes this doesn't happen. This is a fascinating scientific problem. It's a predictability problem. If I can take a computer model with the same environment and get two different results, that should give forecasters like a nightmare, because that means we may not be able to predict as well as we think we can. Here's another interesting view. Let me pause it. So what you're seeing here, now we're looking towards, we're looking north. So what I wanted to show you is, so this is the scale in kilometers. This is 1 kilometer from here to here, okay? That's like 0.6 miles or so. It's the same scale vertically. Do you see these vortices that are horizontal and that kind of take a sharp bend and go upwards? This is kind of a new, as you read the literature, you see more talk of these rapidly turning or rapidly tilting vortices, that they take a sharp turn upwards into the updraft. This is shown beautifully in this simulation. You've got vorticity that's rolling like this, like someone taking a rolling pin and rolling it along the ground. and it's being tilted upwards. And there's a tremendous amount of horizontal vorticity, even it built into the environment for these storms. This updraft is managing to consolidate it, basically strengthen it from almost all directions, tilt it upwards, and stretch it. It's fascinating. So there's a whole bunch of interlocking parts here, but some things, just kind of show up and they kind of make me go, wow, we got to look at this more. So I'll get this going again. So if a tornado hasn't formed yet, you'll see it do its thing. I've sped it up a little bit. I've got so many frames, I can't show them every frame without speeding it up. So notice how everything seems to get, hard to explain, but like suddenly you see all these linear features as all these vortices kind of get lined up, and then there's our tornado. So, every single frame in this image is something to look at. There's all sorts of analysis to do, and we're just starting to peel away some of the pieces here. We see things that we just never dreamed that we'd see in this data. I was talking to one of my grad students the other day, and he saw Kelvin-Helmholtz billows in the cold pool. Now, Kelvin-Helmholtz billows tend to form in the environment where you have an abrupt region of wind shear, where you see clouds that have like breaking waves. We see breaking waves near the ground in this simulation. So here's one more view of this at the 1/6 resolution second, looking at the streamlined vorticity current. So here we're looking west. This blob thing, what we have identified, this is air that was in the forward flank cold pool that's been consolidated, and it's rotating horizontally, and then it gets tilted upwards, and it's rotating vertically. It actually forms much of the mesocyclone, it appears. So this is a very important feature. What it does, and this is where we're at this research, is it helps to lower the pressure locally. There's like a bulge of low pressure that occurs within the region of the SVC. What that does is it increases the vertical pressure gradient that makes the updraft stronger, that helps to support the tornado. You need a strong updraft to support along an EF5 tornado. And you see values stretching. So if you look at the scale here, we got from like 10 meters per second, 50 meters per second, less than a kilometer above the ground. It's incredible. This is the entire vertical domain. I'm zooming in a bit though, before the tornado forms. So here's the updraft in red, vorticity in yellow, and downdrafts in blue. I'm showing this to focus on the rear flank of the storm primarily. We talk a lot about RFDs in supercells. This is the 15 meter per second isosurface. So that's like, say 35 meter per mile an hour downdrafts. Where you see these yellow blobs there, that is downdraft air that is hitting the ground and spreading out. We see interesting things happening in the rear flank that do not appear to be involved with the tornado. They seem to be secondary, and this is an interesting discovery that we're still working on. Here we're seeing the tornado later in the simulation. It's a two-celled tornado, and this is what tornadoes apparently look like in the real world. Most tornadoes, we believe, are two-celled, meaning they have multiple vortices involved in them like this. And we have these two intertwined vortices, both rotating cyclonically, and it's fascinating. Much of the vorticity that becomes vorticity in the tornado is coming from the cold pool. Here's the rear flank. So here's like a rear flank surge, lots of anticyclonic vorticity. It kind of blasts in, but here's that tornado just cranking along. And I could watch this all day, and believe it or not, I probably have a few days. But isn't that fascinating? This is just a simulation. The computer is just integrating the laws of physics. I'm not doing anything to guide it along. Another view where we're starting to see these vortices are actually forming rolls. And again, that tilting into the tornado couldn't be more obvious. I mean, there it is, right? So there's definitely horizontal vorticity embedded within the cold pool that is being stretched along its length while it's horizontal, and it's being bent upward very quickly becoming vertical vorticity where it can be more tornado-y, right? Because that's what our tornadoes do. So all of this vorticity, all the red is cyclonic. When you see blue, it's anticyclonic or counterclockwise vertical vorticity. So there's plenty of that in this storm too. In fact, this simulation does produce an anticyclonic tornado. And in fact, was it Gary who mentioned the tornado? I didn't even know there was an anticyclonic EF4 until I heard about that one the one near Milwaukee. I'm gonna have to study that one. Anticyclonic EF4s are very, very, very rare. I don't think there's ever been one stronger than that. Early in my work on this simulation, I got anticyclonic EF4s and I was going to shoot myself because I thought the model was backwards or something. Anyway, you don't see too many anticyclonic tornadoes. Here's later on in the simulation, and this is when the tornado's getting weaker. It's sort of spreading out. You can see the multiple vortices here, but look at this blue guy. There's this anticyclonic vortex that seems to just come out of the air, grows out of the ground. And this thing is going to go around the main red tornado, the cyclonic version, and it's going to do some fascinating things. I should just shut up and show you, but essentially this thing just goes around twice. If you had to forecast this, I mean, think about it. This is a simulation of a physical phenomenon that is plausible. How important is that? If you're standing there, you're going to get hit by that would be normally called a multiple vortex tornado. That is an anticyclonic vortex that is, yes, it is being supported by the same updraft that's supporting this tornado. But look at how they interact. The blue guys and the red guys fight, just like politics in the US. I made that joke last time, by the way, so it's not going to be very good. But anyway, so these guys the blue guys essentially get advected around the tornado and do all sorts of things. When you have the red guys coming together, they merge together. So you're consolidating vorticity. But this is the same sequence from two different views, 4 times faster. So just watch the blue one, watch how it gets twisted around. It actually sort of cuts right through the cyclonic tornado, and the cyclonic tornado kind of burps, and after this thing's done, it takes off again. But there's definitely a destructive mechanism involved when you have the anticyclonic tornado or vortex interacting with the cyclonic. So, you hear these stories of a house gets completely wiped out, 3 houses down from you, and your house barely got any damage. Something like that could have been happening, right? It's one possibility. There was a vortex that was, maybe an anticyclonic vortex that was just getting stretched at the right time, boom. Or it's a multiple vortex EF5, where the vortices are actually literally attached to the cyclonic part of the tornado. They're part of the tornado. And this looks a little bit like Rochelle, I thought. This is another simulation of the same environment that I've been working on. You've probably all seen this video filmed by Aaron Rooney, who got stuck on the side of I-39. This is the Rochelle tornado as it crosses, or the Fairdale as it crosses the road. But the reason I show this, and you'll see this, I'll freeze it. Notice we have multiple vortices in our simulation, and hopefully it'll show up. I'll pause it, but you can see multiple vortices occurring within there's one right there. You can see the atmosphere. You can see evidence of lack of cloud in here, so you'll see another one. So I put these side by side because I think, wow. There's another one. So there's his wiper blade, but there's another vortex. You see the same thing down here. To me, that is tremendous. I mean, it blows my mind that it looks that good, honestly. This is the highest resolution simulation I've done yet. So this is the one that's 15 meters or 12 billion grid points. It looks a little bit more messy, as you might expect, than the 30-meter simulation. Here's our cyclonic tornado. Here's our forward flank with our clouds streaming in. You'll notice in this simulation you see more individual cloud elements sort of rising up into the storm, evidence of that strong updraft, but it's also evidence that you're resolving things better, and the tail cloud is more of a kind of a collection of clouds, but the tail cloud doesn't always look like this, but I found this interesting. Here's some extremely strong downdrafts that occur in the rear flank. These downdrafts are interesting because you see the rain, this is rain, and you might think the rain is causing the air to, dragging it, all these things we learned about downdrafts. What I think is happening is there's some dynamic forces that are pushing the air down and basically dragging the air down basically along for the ride. It's almost like the air is being pushed to the ground, which is bizarre. Again, the blue here is the cold pool, the red air is warm air, and this air is the atmospheric air. So we have air in the rear flank where you typically expect it to be cooler, actually warmer from compression as the air sinks. Meanwhile, this tornado's getting pretty crazy. It gets even crazier. You'll see in a few minutes, there's a second tornado that'll form right about here. That's an anticyclonic tornado, and I will call it a capital T tornado. It's definitely not just a anticyclonic vortex. And you're going to see it form. Just keep your eyes right about here. You can already see the anticyclonic type of motion, but there we go. And what the heck? I saw this, I'm like, you got to be kidding me. And then I watched it a little more, and I'm like, seriously? You're going to dance? I mean, they look like they're having a little get-together. You have 2 tornadoes dancing around, and then, okay, thanks, see you later. So these simulations, the fact that we're seeing this sort of messiness, this sort of chaotic stuff that you sort of see in Mother Nature is actually a good sign. It means our models are probably contain a lot of the necessary stuff that we need to get this right. But we don't have trees, we don't have houses, we don't have debris, we have rain in our tornado. I mean, I could sit, it's sort of like everybody can always point at the most, the critical things in their own work, right? It's so easy to pick those out. But there are some things we need to work on. But on the other hand, there's enough that we're getting right that I feel like we've got this. We're in pretty good shape here. So this is the vorticity again. This is the streamwise vorticity current coming in. It's definitely more messy than it was. You can see all these individual vortices kind of comprising this mess. Here's our anticyclonic tornado we were looking at earlier, the one that starts right away. And if you look really closely, out of this mess of red, you will see a big tornado start to form. There it is. So, like I said, where's the trigger? You know, is there anything that we saw before that we could use to predict that it was going to happen? And that's where our research is, right? I mean, that's one of the directions our research is going. At this point, we're just trying to understand this crazy simulation with all this amazing data, or several simulations. Here's a view looking along the SVC, and you can see that rotation beautifully. Here's this big mess of stuff, but it really is rotating. It's rotating horizontally, it's being tilted, and rotating vertically in our tornado. Okay, so for the rest, about next 3 minutes or so, I wanted to intersperse. This is something that Hank Schima did. He did a little YouTube interview with me, which was a lot of fun, and he did a section of his presentation where he compared some of my model simulation work with his observational work, and I think this is wicked cool. So we'll start out with the tail cloud, or your ghost train type cloud that's streaming in from the right. And there it is in one of our simulations. That looks good. Looks like we got that pretty well. Here's our vorticity field. So here we're looking at, on the left, I'll pause it. This is a similar view as to before. Here's our big tornado, our cyclonic tornado. Here's an anticyclonic vortex, cyclonic, anticyclonic, duck, duck, goose. You know, there's a whole bunch of stuff in there. We see evidence of little tiny vortices that aren't tornadoes in real storms as well. And this is the kind of thing that I'm always, when people talk to me about what should I be looking for if I go chasing, I'm saying, well, keep an eye on the forward flank and look for little vortices. I mean, again, I'm being selfish here, but I'm saying there's interesting things going on. And, you know, I'm not saying that that's super important, but it might be. Here's where Hank compares the sort of the turbulent growth of the cumulus turrets to a time lapse of his own. Wall cloud looks pretty good. Rotating wall cloud, and here's another version of the tail cloud that looks really good. Oh, it doesn't show up too well, but there's just a screaming tail cloud. A very barrel-like sort of laminar type mesocyclone at low levels. You see that as well in many cases in supercells. A laminar region that is overlaid by a turbulent sort of, the clouds start to really rise freely, turbulently. And finally, we have multiple vortices in abundance, And this next actual video is from Wynnewood, I think. One of my favorite tornadoes recently, at least from a photogenic perspective. Lots of interesting things. There's some horizontal vortices and vortices being twisted around. Here's a view through the forward flank, or the rear flank, where you see the tornado is completely rain-wrapped and it's obscured, and then it kind of peaks out for a little bit, and then it kind of gets obscured again. I don't know how he did it, but Hank found something that did exactly the same thing from the rear flank. He's in the rain a bit. You can see the tornado, it looks pretty good, and then suddenly it's gone. It's been obscured by rain, and then it sort of reemerges later on. Anticyclonic funnel I talked about earlier. Technically, it might be a tornado. I haven't looked at it too closely yet. We see these in Mother Nature as well. There was a really photogenic one in Colorado a couple years ago that was just absolutely beautiful. And this I had to do twice. I thought it looked so cool. Mammatus clouds, real mammatus clouds, fake mammatus clouds, storm mammatus, simulated mammatus clouds, and then the real ones again. But I love that because it looks pretty good. You know, again, I have to look to Mother Nature because otherwise it's all just screwing around on the computer. You got to compare to the real world. Finally, this last sequence here, it looks kind of like a streamwise vorticity current. You've got clouds along the forward flank coming in and rotating, and here is the same thing that we see in our simulation. So over the next minute or so is kind of putting stuff side by side. I thought that was kind of cool. You blend in a stovepipe tornado to our simulation, looks pretty similar. It's a real nice way to sort of look at where the state of the art is right now. What's on the left is clearly fake, but it's like, all right, it's doing all right. You know, it looks, the gross characteristics are pretty good, and in fact, when you run at higher resolution, it gets even better. Someday I want to get debris in there. That's going to be a very complicated matter because debris follows its own laws of physics that the air doesn't. So you have a mixed phase environment, and that's a real challenge. The same problem comes with trying to get the rain out of the tornado because you have to treat rain differently by virtue of its mass. So anyway, I hope you've enjoyed my talk. Just a few parting thoughts. We can do this now. I mean, here it is. That's kind of an obvious statement, but I would say that for those of you who have been maybe following this, the research in meteorology for years, we couldn't do things like this until recently. We simply didn't have the power. I've been working on this problem for over a decade, and I started working on this before Blue Waters was even thought of. I just knew that I was going to have to deal with a tremendous amount of data in the future, so how am I going to organize this data? And I found a way to do it that works okay, and I can do stuff like this. So as far as where this research is going, I'm still spinning up, got students working with me. We want to look at more storms in 24 May because obviously we can't make general statements about a single storm. That's not the way the science works. And my computer just went to sleep, but we're pretty close anyway to the end. And finally, from an operational perspective, I put this statement in recently because I gave a talk to operational meteorologists. I don't think that this research particularly, we won't really benefit from it, although we're getting there, as Gary said. We really won't benefit from this research for years. In meteorology, research often goes in fits and starts. Sometimes there'll be a Vortex field project, tells us a tremendous amount about storms because we went out and measured them. Then I have to catch up with my model to get to their level. And then I have this simulation, and it blows everyone's mind. And well, they got to go find those things now in the real atmosphere. So that's what's so cool about meteorology. It's not like astronomy, which is another one of my favorite fields. You can't go out and check if that star, it's a billion light years away. You can actually measure things. So you have this theoretical aspect, the danger aspect, and then the majesty of the atmosphere aspect all tied into one. And it's got computers too, so I'm just happy. But anyway, finally, but we're going to get to the point where we can give better warnings down the road. It has to happen. I want to acknowledge my collaborators on this project, Kathy Finley at St. Louis University, Bruce Lee, High Impact Weather Research and Consulting LLC, Robert Wilhelmson, one of the pioneers of cloud modeling at the University of Illinois, now retired, my grad students, Austin Dixon, Kelton Halbert, and this is supported by a couple of NSF grants, including the Blue Waters machine as well. So obviously, in all seriousness, I won't get political, but I'll say thank you for spending for tax dollars. I mean, there's a lot of good things done with tax money. Let's just leave it at that. And I'd be happy to take any questions, and if you want to see cool movies and stuff, there's my website. This talk will appear with my audio on it, assuming it recorded well, in a day or two if you want to watch it again. So thank you very much.
I just have a comment because when you talked about the multiple vortices and the dancing thing years ago on the Weather Channel, I saw that exact same thing, and they made the comment that the Kansas Indians at the time had a name for that. They called it dead men walking. So apparently it's something that they'd observed throughout the years.
I've got to catch up to that then. Yeah, exactly. I got to read the right journals. That's really interesting. The fact that anyone had ever given something like that a name blows my mind. Yeah. I mean, I've seen that in visual footage before, but in the simulation, I was just like, you got to be kidding me. I mean, I can't wait to unpack what's really going on between those vortices when I get in there. But.
Anyone else?
All right. There you go, Gary.
Thank you very much.
Absolutely. Yeah.
Let's even go and watch the Weather Channel sometimes.